All right, let's talk about Chapter 7, which is on ocean currents. So firstly, there's two types of currents. There is the surface currents, which only flow at the surface of the ocean. They are driven by wind, so that's how they are created, is you have to have a sustained wind over the surface of the ocean in order for them to occur. In that map there, you can see that there are two types of surface currents. You have the arrows in red, which represent currents that carry warm water from place to place, and then you have the blue arrows, which represent cold water currents. So they move cold water around. So generally speaking, what you'll see is the blue arrows. They carry the cold water from the polar regions up to the equator, where it's warmer. So effectively cooling down the equator region. And then the red arrows, generally speaking, you'll see them starting in the equator and moving warm water down to the polar regions, and that effectively cools off the polar regions, right? And then next, you have deep water currents, and those occur in the deep ocean, and they are created by differences in density. So when you have surface water and deep water, your surface water is going to be less dense compared to your deep water, because your deep water is going to be under more pressure and it's going to be colder, so your water is going to be more dense compared to your surface water, which is warmer and under no pressure, so it's therefore less dense. But in order to create deep ocean currents, which we will talk about later on in these slides, you need to have a rapid increase in density of the surface ocean water that will then rapidly sink and then start off your deep currents. All right, so some different ways to measure currents in the ocean are your direct methods and your indirect methods. Your direct methods are your floating devices and your fixed propellers. And we'll go over this in the following slides. And your indirect methods are your pressure gradients, your radar altimeters, and your Doppler flow meters. So your floating devices, we will talk about your direct methods first, but your floating devices are exactly what's depicted on the slide here. You basically have a buoy, and the buoy floats on top of the surface of the ocean, and it follows the current. So the current pushes it as it's flowing, and that white piece on top of the buoy has a radio transmitter, and as this buoy is flowing along the current, it's taking measurements, and it's calculating how fast it's going. And so when it gets from point A to when it's released into the current, and then the boat will determine a certain distance, and then once that buoy gets to that distance, they will take the buoy out, and they will look to see how long it took the buoy to get from point A to point B. And depending on how long it took, they can determine how fast that current is moving. So likewise, if it's a really fast moving current, you should expect that buoy to get to the end point really quickly, versus if it's a slower moving one, it's going to take its time. Next, you have your fixed propellers, and these are they look just like miniature propellers that you would see on boats, and these have to be fixed to a specific location, so they don't float in the water like the previous one. So a lot of times they will be either attached to some sort of buoy device, or they'll be attached to the bottom of the ship. And what you, well, not to the bottom of the ship, sorry, but something that's fixed in place. So I can't think of something right now, but it's fixed, and essentially what it'll do is the current, it'll be placed within the current, and as the current flows, it'll spin the propeller, and depending on how quickly that propeller spins will determine how fast the speed of the current is. So obviously if it's a faster moving current, it's going to spin that propeller much faster than if it was a slow moving current. Alright, so those were the two direct methods, and now for your indirect methods you have pressure gradients. And these pressure gradients take advantage of the differences between the high and low pressure atmospheric pressures that can cause the surface of the ocean to either go up, increase in height or decrease in height. And so when you have low pressure, you can assume that the water level is going to be lower, obviously. And then in high pressure, you're going to have a higher water level. And the difference in height between the high and the low pressure regions will cause the water to flow from the high to the low. And when you do that, that's what's known as pressure gradient. So you create this current between the high pressure and the low pressure. And that current is going to flow downhill, much like on land, when it's raining, you see water flowing from the top of a small little hill down to the bottom. And that's because of gravity, right? So this particular flow isn't caused by some sort of wind or anything. It's purely caused by the differences in the pressure, and so gravity will pull that water down to try to equalize it between the high and the low pressure. Hopefully that made sense. So here's another graphic. You have high pressure on the left hand side, low pressure on the right hand side, and this is just a depiction of what is going on between your pressure gradient, the movement of the water, which is called motion, and your Coriolis, right? Everything on Earth is affected by Coriolis, and so your Coriolis is always going to be 90 degrees of the water direction, so the motion, okay? So you'll start off with the box next to the high pressure, and you can see that the water movement goes from high pressure to low pressure, as well as the pressure gradient force, which we can talk about later. So both of those will go from high pressure to low pressure, but your Coriolis goes 90 degrees from the movement, the motion. So that's why it's pointing down. If you go a little bit further, so you go to the next box down, you see that the pressure gradient force does not change. It will always go from high pressure to low pressure no matter what. But at this point, the Earth is spinning, so you can expect that the water flow, the motion, is going to change. Okay, so you can see here that it changed, and now it's going in a southeast direction. Okay, but your Coriolis takes a little bit of time to adjust, so it's still pointing down. So when you move to the next box, it finally adjusts, and it adjusts in a way that becomes 90 degrees of the motion again. So it's kind of going off in this weird southwest direction. And again, your pressure gradient force, the PGF, doesn't change. It always goes from high pressure to low pressure. So, the Earth is continuously moving, so the water motion adjusts one more time, and so now it's pointing south. And likewise, your Coriolis has to adjust, so now it's pointing in the complete opposite direction of your pressure gradient force. Right, so your water movement is going to be 90 degrees to the right of your Coriolis, which then your pressure gradient force is going to be 90 degrees to the right of your motion. Then you have radar altimeters. So radar altimeters are usually found on satellites. You can find them on airplanes too. And the altimeters measure the pressure gradient from space. And so they look at the difference between the high and low pressures. And they calculate what the current speed is from that. So a lot of that calculation is done using computers on the satellite, but they use that same radar that they use to measure the ocean depth. They also use it to measure how quickly the currents are flowing. And then lastly, you have your Doppler flow meter. And this one is generally not used in the open ocean. Typically, you'll find these in pipe situations. So typically, sewage treatment plants and other, like the water company, will use these types of sensors. And yet, as you can see in the photo there, it's attached to the outside of the pipe, and it uses sound. So it transmits the sound down to the bottom of the pipe, and it's reflected back. And and then it looks to see how quickly that sound wave came back to the sensor. And depending on how quickly that sound wave came back, it can determine the water speed within that pipe. Now, granted, the particles within the water can reflect the sound waves, so it could delay or it could give an error in the current speed. So typically, clear waters would be the best to measure this. Okay. So those are your types of measurements. They do some measurements of deep water currents, and they typically will use what's known as or they'll use this type of buoy. Right? This type of buoy descends down to a certain depth, and as it descends, it'll drift. In this instance, it drifts for 9 days, but it could vary. It just depends on how much battery life is within this buoy. Because within this buoy, there's a number of things. You have your computer, you have your battery pack, you have a oil-filled container or chamber that allows the buoy to go up and down. And as that buoy is down at depth, it's taking measurements, and then it comes back up to the surface. It transmits all of the data that it collected to the base station, basically. And then it also most likely has solar panels on it, so it's recharging its batteries. And then once it's done transmitting all of the data, it goes back down to that depth and continues the cycle. So this is a way of measuring deep currents. So as you can see here, this is just a map of the different buoys around the world, and this was back in April 2016. So I'm sure some of these have gone out of commission. There's probably some new ones out there. But as you can see, all the different dots represents a buoy. So There's a ton of buoys in the ocean right now. And what I want you to pay attention to is the different colors of the buoys, and each different color represents a different country, a different country's buoy. So for instance, in the Pacific, you can see a bunch of light blue ones up by Japan, though all of those buoys belong to Korea, and all of those purple buoys belong to Japan, and those dark hunter green buoys, those all belong to the US. Okay, so by far the US has buoys just about everywhere, whereas other countries tend to be more localized to where they're at. You can see in the Atlantic Ocean there's that light orange color, which I believe is France. So France has a ton of buoys all throughout the Atlantic Ocean there. There's a lilac purple in the Indian Ocean, and I'm fairly certain that's Australia. So Australia has another significant amount of buoys within the ocean. So these are known as Argo buoys. Okay, so geostrophic flow, that's when your flow is determined by your pressure gradient, and your Coriolis. So this is a lot of physics, so I apologize for that. And I may make some mistakes here and there because physics was not my best subject, but I will do my best. But essentially what you can see here is the equator, which is in the middle, that middle dotted line. On either side, you can see that the geostrophic current is flowing to the east. And your geostrophic current is flowing to the east because your Ekman transport is going 90 degrees to the right of the wind direction. And so from that, your geostrophic current goes. Your geostrophic currents will be going in the resultant direction of your wind and your Ekman transport. So in this case, this is without any continents and a rotating Earth. So when you have that, the currents near the equator will be flowing in an easterly direction, while the currents on either side of that would be flowing in a west direction, and then you would rotate to an east direction in the polar regions. And that's because your Ekman transport is 90 degrees from the wind, so therefore your current direction will be going either east or west from that. Okay. Some facts about current. So actually, if we go back, the reason why that works in a situation where you have no continents is because there's nothing obstructing them. The reason why our currents that we have in our ocean today look the way that they do is because of the continents that we have around the world. And so because of those continents, they deflect the currents and wrap them around and eventually create gyres, which we'll talk about later. And so some facts about currents. Only about 2% of the wind's energy is transferred to the ocean surface. So if you think of the wind blowing over the surface of the ocean, only 2% of that wind energy that's blowing over the ocean surface actually transfers into the ocean. Continents also play an important role in how surface currents form, which I mentioned, and apparently there's a video. Okay, well, I'm gonna have to work on. I'll create a link for you so you can check out that video. And then in the ocean, so surface currents, you have these main types of current: ocean surface or ocean currents. So you can have subtropical gyres, you can have equatorial currents, you can have western boundary currents, north and south boundary currents, eastern boundary currents, and equatorial countercurrents. So let's talk about each one. So subtropical gyres are very large moving currents, and they incorporate the north and south boundary currents, the eastern boundary current, and the western boundary current. So your subtropical gyre is the current, basically the ocean basin current that moves water in a circular direction, circular movement, I should say, and it moves the ocean water around that ocean basin. Basically, it moves it around that ocean basin. And these are driven by wind, and the center of the gyre generally coincides with the 30-degree latitude line. So in that image there, you can see the North Pacific gyre. The center of it is more or less around 30 degrees north. Your South Pacific gyre generally is at 30 degrees south, and so forth and so forth. So there's 5 major ocean gyres. You have your North Pacific gyre, your South Pacific gyre, your North Atlantic gyre, your South Atlantic gyre, and your Indian Ocean gyre. So the Indian Ocean only has one gyre because majority of the ocean is in the southern hemisphere. In the northern hemisphere, you can see it's all continent. Okay, so firstly, you have your equatorial currents. So these currents are found at the equator or surrounding the equator, and they move water from a east to west direction. All right, so they always start in the eastern side, and they move water to the western side, and they move warm water because the equator is warm towards the west side of the ocean basin, and they all move in that direction. And these particular currents are created by trade winds. Then you have your western boundary currents. So those are the currents on the west side of the ocean basins. So that's like your Gulf Stream, your Kuroshio current in the Pacific, and your East Australian current. So if you guys are familiar with the movie Finding Nemo, you guys all should be familiar with the, was it EAC? I believe it was the EAC, right? They threw around that acronym quite a bit in the movie, and at one point they explained that the EAC is your East Australian current, and that's one of the currents that they use to get around. So these western boundary currents are created by the deflection of the equatorial currents by the continents and Coriolis. Okay, and so they still are warm water. So they start near the equator and move water up to the polar regions. And so these particular western boundary currents are very fast, as you might remember from Finding Nemo, and they are very deep. So they're not very wide currents. So they're very thin currents, but they're very deep, and they're very fast moving. So they move a lot of warm water up to the polar regions on a regular basis. Then you have your northern or your southern boundary currents. So depending on what hemisphere you're in, these ones are going to be opposite of the equatorial currents. So in the North Pacific gyre, you can see the North Pacific current. That is going to be your northern boundary current. So in your northern hemisphere, you're always going to have northern boundary currents. In your southern hemisphere, you're going to have southern boundary currents. And that's just because of where these currents are located and depending on what hemisphere you're in. These particular currents are created by westerly winds, so they are wind driven, much like the equatorial currents. And depending on which hemisphere you're in, you can either have warm, or you can have it transporting warm or cold water. So in the Pacific, or not Pacific, in the northern hemisphere, it typically transports warm water. So you can see the North Pacific Current and the North Atlantic Drift. Both of those carry warm water up to the polar regions. Whereas if you look in the south, the southern hemisphere, you can see the West Wind Drift. That is the current, that the southern boundary current that makes up the South Pacific Gyre, the South Atlantic Gyre, and the Indian Ocean Gyre. So that particular current carries cold water. And then lastly, you have your eastern boundary currents. So like it suggests, these currents are found on the eastern side of the ocean basin. So these particular currents are slower moving. They do carry cold water from the polar regions down to the equator, and they tend to be wider and not so deep, unlike the western boundary currents. So all of those currents in blue, such as your Peru current, your California current, your Canary current, or your West Australian current, those are known as eastern boundary currents. And again, like your western boundary currents, these eastern boundary currents are created by Coriolis and the deflection of the continents. So in the South Pacific Gyre, you have your west wind drift that gets deflected by Coriolis and by the deflection of the continents, and it turns into the Peru current. And next you have your equatorial countercurrent. So in the image below, you have in between your North Pacific Gyre and your South Pacific Gyre, you have your north and south equatorial currents. Well, in between that, you have an equatorial countercurrent, which flows in the opposite direction from your equatorial currents. So why is that? Essentially what happens is your north and south equatorial currents pushes water from the east to the west side of the ocean basin. So what ends up happening is you have a piling of water in the western side of the ocean basin. So over in that Pacific, you can see that, if you can imagine, water is piling up near Indonesia. And as the water piles up over there, it creates a high, right? Basically a hill of water. And so what ends up happening is that hill of water then creates a geostrophic current, which then sends water back in the opposite direction, and that's how you get your equatorial countercurrent. Okay, hopefully that made sense to you guys. Then you have your subpolar gyres, and so this one is created by the westerlies, and it rotates in the opposite direction from your subtropical gyres. So pretty much the main one is in the Pacific, which is just north of your North Pacific Gyre. I believe there's a smaller one in the Atlantic, but you probably don't have one in the Indian Ocean, right? So your North Pacific Gyre rotates in a clockwise fashion, whereas your subpolar gyre in the North Pacific flows in a counterclockwise direction. Okay. And your geostrophic currents, so again, they go from high pressure or high to low. So when you look at the right image there, you can see a little bump or a little hill of water being created. So at the very center is where you'll have your high, and when you get down to the bottom of that hill, that's where your low is at. So water is going to flow from the top of that little mound of water and down the slope all the way to the bottom of the hill. But don't forget about the rotating, the earth rotation. So when the earth rotates, it's causing the water motion to actually rotate around that mound of water. So instead of going from the center, the top of that hill down to the bottom, it's actually rotating in this example in a clockwise direction, because you have your pressure gradient going from high to low. Then your Coriolis is just the opposite. So it goes from low to high. And then your water direction is just going to be 90 degrees to the right of your pressure gradient. So it's going to rotate. So it's going to flow with a clockwise direction. Okay, as the black arrow suggests. So that's the reason why the North Pacific Gyre follows this example right here. So in the middle of that gyre is where you have your high, and everywhere else in the other continents is going to be your low. So your water direction rotates clockwise. In the South Pacific Gyre, it's just the opposite. Okay, and that's because you're in the southern hemisphere. So pretty much gravity and Coriolis leads to geostrophic currents. Then there's this thing known as the western intensification. So if everything was normal, I guess nothing unusual was happening, or if you don't have Coriolis, then you would expect your gyres to look like the image on the left hand side there, where everything is uniform. The center of the gyre is in the middle, and as you spread out from the center, it's all evenly spaced. But because we have Coriolis, the center of the gyre is actually offset. So the center is actually closer to the western side of the ocean basin, which is the reason why your western currents are faster and tend to be deeper and tend to be more narrow than your eastern currents. So your eastern currents are much more slower, much wider, as the image on the right hand side depicts. So here we're looking at the different regions, climate regions on the Earth's surface, and you can see the red and blue arrows overlaid on top of those climate regions, and how currents affect climates of nearby regions is because they can affect the air temperature. So for instance, let's look at the west coast of the United States, and you can see a blue arrow coming from Alaska and going down past Mexico. That blue arrow is carrying cold water from Alaska down to the equator. So when it's moving cold water down, it's affecting the air temperature. So the air temperature on the west coast tends to be cool, especially at nighttime, cool and drier, right? Whereas if you look on the east coast side of the United States, you see a red arrow, which means it's taking warm water from the equator up to the North Atlantic. And so the areas on the East Coast tend to have more humidity and tend to have warmer climates. And that's because of that warm Gulf Stream that's passing by the states there. So if you guys ever wondered why New York during the summertime is super humid, It's because of the Gulf Stream. And if you ever wondered why San Francisco tends to be foggy and cold even during the summertime, it's because of that the cold current coming down. Okay, so Ekman spiral. This describes the speed and the direction of surface waters at various depths. So depending on where the wind is blowing will determine where your Ekman transport is at. So basically just where the water direction is going to. So in the top image there, the wind is blowing, let's just say from north to south. And because it's blowing in that direction, your Ekman transport is always going to be 90 degrees to the right of your wind direction. And so the 90 degrees to the right of the wind direction is offshore. So as the wind blows, it's pushing water out into the open ocean, into the deep ocean, and it's causing water to come up from the deep to replace the water that's being pushed offshore. Right? So in this case, this is what you have. This is what's known as upwelling. So areas like Peru, off the coast of Peru, there's an upwelling region where water is transported offshore and replaced by water from the deep. And that water from the deep is nutrient rich and leads to high biological productivity. So a lot of fish. Whereas if you look at the example on the bottom, you can see the wind has shifted and now is going from south to north. And that Ekman transport is going into the coastline there, right? Because it's 90 degrees to the right. So because it's going towards the shore instead of going towards the open ocean, it's causing water to pile up near the coastline, which then causes water to sink because it's getting heavy. And this is what's known as downwelling. So this is what happens off the coast of Peru when you have El Nino events. So it basically shuts off upwelling, so no more nutrient-rich water coming up. You have water going down. Then you can have diverging and converging waters. So at the equator, you have your trade winds coming up, which is causing the water to go away from the equator, which then causes an upwelling at the equator itself. So you have water diverting away from the equator, which then has to be replaced. So water from the deep comes up, and you tend to have high biological productivity at the equator. Likewise, you can have converging waters. So this is what happens in the western side of the ocean basin, where water piles up, or when you have downwelling events. And so the water piles up on top, it becomes heavy, and it causes water to downwell, so to sink, basically. So that's how you can have upwelling and downwelling areas in the middle of the ocean. Next, we have cold and warm water rings. So let's just use the Gulf Stream as an example, because it is a really fast moving stream, and it's pretty well studied. And what you can see in this image here, and this is a image of the Gulf Stream and looking at the sea surface temperatures. And so you can see in the bottom left hand corner there, the really dark red colors represent really, really warm water, whereas your blue colors up in the top right hand corner there represent really cold water. So you can see here that the Gulf Stream transports that really hot water from the Gulf of Mexico up to the North Atlantic region. And in doing so, the Gulf Stream typically will follow the coastline until it gets to, I guess that would be Newfoundland up there, at which point then it leaves the coastline and goes out into the open ocean. And when it does that, because it's such a fast-moving current, it meanders much like a stream does on land. And when it meanders, it creates these rings, and those rings eventually will snap off or pop off from the main current and continue rotating and traveling around the ocean. So, for instance, that small little cold water ring in the middle of that image there, that's surrounded by warm water, and it's rotating in a counterclockwise direction. And it's moving that cold water around the ocean. And so that cold water typically will be nutrient rich. And it's going to have organisms within it that rely on cold water. And so as that cold ring is moving around, it's moving around those nutrients. Likewise, just north of that, you can see a round red ring. That would be known as a warm water ring, and those rotate in a clockwise direction, and they move warm water northwards to cool off that region. Okay, so now next you have monsoons. Monsoons, typically you'll see those within Southeast Asia, and they are dependent on what's known as the Intertropical Convergence Zone. So this zone causes a lot of winds and heavy precipitation when it's over land. So in June and July, you tend to see a lot of heavy rains, especially like in India and Thailand and Indonesia, because it's bringing warm, moist air up to or over the continent. And when it does that, it creates a low pressure over the Asian continent, which then causes a lot of precipitation. Okay. And then in the wintertime, it goes back, it goes south, and it creates a high pressure over the continent and dries everything up. So try not to go traveling to Southeast Asia during the summertime. Wait till the winter time when it's much drier. Then we have this phenomenon known as the Walker circulation cell. This Walker circulation cell occurs, it's a factor of conditions within the atmosphere affecting oceanic conditions in the Pacific. And so this is what it would look like normally. So normally near Indonesia in the western side of the Pacific, you'll experience very humid conditions, and it'll tend to rain a lot because you have warm water, and that warm water heats up the air in the atmosphere, which then causes it to rise, creating rain clouds, and so it rains. And that air will then travel all the way back towards South America, where it has cooled off and then starts to sink. And so that cool, dry air then sinks back down to the ocean surface, where then it travels back towards Indonesia, where it warms up, and it cycles like that over and over again. But in the ocean, you tend to have a similar thing happening. So because of that atmospheric, because the air is doing that circulation, you tend to have upwelling near South America, because that wind is pushing all of the water towards Indonesia. So you have an upwelling near South America, because that water has to come up and replace the water that's being pushed over towards Indonesia, where that water over by Indonesia will downwell. So you have water coming down by Indonesia, and you have water coming up by South America. So you have this whole cycle, not only in the atmosphere, but also in the ocean. Okay, so these are under normal conditions. Now, what happens when we have abnormal conditions, which a lot of you may know as El Nino. So El Nino is short for El Nino Southern Oscillation. So that's ENSO, the acronym ENSO, ENSO. And El Nino, so there's two parts to ENSO. There's El Nino and La Nina. And essentially it just means the boy and the girl. All right. And it was primarily named that way because of how this type of phenomenon affects fishermen in Peru. And because Peru is a Spanish-speaking nation, that's where these terms were coined from. So during El Nino events, you have to take the Walker circulation cell that we looked at in the previous slide, and you have to reverse that. So you instead of having your high pressure area near Indonesia, you have to reverse it, and now you have your high pressure over South America. So instead of cool, dry conditions in South America, you will have humid and warm conditions. All right. And that will cause a lot of rain in South America. And then over in Australia, you'll have your low pressure. Actually, no, I'm sorry. Low pressure is over by South America. Then you'll have your high pressure over by Indonesia and Australia. And you'll have cool, dry conditions, which they're not accustomed to. And then the warm pool, which is where all the warm water was near Australia originally, now travels back across the Pacific Ocean towards South America, cutting off that upwelling area and causing a downwelling effect. So you have upwelling near Australia, and you have downwelling near South America in this case. So because of that, you don't have that really steep thermocline anymore. You don't have that upwelling, and the conditions are reversed. Your wind direction is reversed too. So it not only affects the fishermen in Peru, but it affects the water temperature and the atmospheric conditions as well. So here in Hawaii, during El Nino events, we tend to be more dry and more hot than normal, which is terrible. I don't know if you guys remember how hot it was back in 2015. That summer in 2015 was really bad. I remember going out and getting an AC during that summer because I couldn't take it. And then La Nina is just it's just take your Walker circulation cell, so your normal condition, and you just increase that initial condition. So you have a strengthening of the wind. So you have a strengthening of the high pressure over South America, and you have the strengthening of the low pressure over Indonesia and Australia. So you have, they tend to have more rain in Indonesia during La Nina. We also experience more rain here in Hawaii during La Nina conditions. So right now, last year and this year were La Nina years. And so here in Hawaii, we experience more rain during the summertime, which you guys should have noticed. And it's also a little bit more humid as well, too. And so I typically prefer La Nina conditions because even though summertime is still hot, you do get more rain, which tends to cool off the weather a little bit more over here in Hawaii. But so essentially you're just strengthening that walker circulation, so that warm water pool that you see in the west there, that is further pushed into Indonesia, and more of that cold water comes up from the deep near South America. So some effects that ENSO can have in the ocean, it can affect the jet stream. So depending on whether it's El Nino or La Nina, it can affect whether the jet stream is fast flowing or if it slows down. Typically you can see unusual weather patterns. So like here in Hawaii, we can go from like super drought conditions in El Nino to super wet conditions during La Nina during the summertime. Well, during the summertime and during the wintertime. During El Nino here in Hawaii, during the summertime it's really hot, like really, really hot, and there's not a whole lot of rain during the summer. And during the wintertime, it's warm. It doesn't really cool off. Versus La Nina, we tend to experience a lot more rain during the summertime, but we also see cooler conditions during the wintertime here in Hawaii. And because of these extreme events that El Nino typically exhibits, you can experience extreme flooding events or extreme drought, depending on which one, whether it's El Nino or La Nina. And because of those droughts, you can see more fires. So in California, they've seen an increase in their fires every summer, and that's partially because of El Nino. And then you can also see a lot more tropical storms. So if you've noticed over the years, we've been having more and more hurricanes, and that's primarily because of ENSO. And so during El Nino years, we tend to see more hurricanes than we do during La Nina years because the ocean temperature is much warmer. And then next you can have deep ocean circulation. So deep ocean circulation looks at the differences in density. And so you have in the image on the bottom there, you have warm water traveling from the equator up to the polar regions. And when it does that, that warm water will cool off really quickly. It'll transfer all of its heat from the water into the atmosphere. And when it does that, it rapidly cools off. It also probably creates sea ice, which causes the density of the water to increase. So you have this increase in density. You have this decrease in temperature very rapidly. And so when you do that, you increase your temperature very, very quickly. And that water that has cooled off and become more dense will sink. And it will sink into the deep ocean, where it will flow along the bottom of the ocean, and it will create your deep ocean currents. So when you have that water go down into the deep, you are creating what's known as the ocean conveyor belt. So that ocean conveyor belt brings oxygen down to the deep ocean via downwelling areas, and then at upwelling areas, like off the coast of South America, you bring nutrients up to the surface. So that's pretty much the only way the deep ocean gets its oxygen, is from downwelling areas. So it's really important to have these upwelling and downwelling areas. Alright, so that was chapter 7. So stay tuned for chapter 8, which will be on waves.